Hi, this is Sean from 7442 Analytics. This is a tutorial to build this Elliott wave spiral using the raw NASA data imported into the Spiral Calc spreadsheet. So let's move forward real quick. None of this is scripted. Bear with me as we move along. First off, you should know that my background in Elliott wave research goes back to 1983. When I was working on the floor of the Chicago Board Options Exchange. About 1984, I met a guy on the floor. His name was Tony Santoro, and we had discussions. He was an older guy. He made millions of dollars in trading Teledyne options, but he left the floor for various reasons, and I met him up in his office one day, and we got along pretty well. And one day he goes, "You got to learn Elliott wave." So he handed me his copy of the Elliott wave principle. And that kind of started. That was 1984. To me, I thought Elliott wave was very subjective. There aren't any written rules in there. So that was the premise of me creating the time labeling tool to let the colors do the counting based on the time label coloring scheme and strip the subjectivity from Elliott wave counting. So that goes back to 1984 when I was a floor trader in Chicago. So what you see in this image, I have everything inverted for presentation, but what we see in the image is an actual spiral spreadsheet, and I put Prechter and Frost's book right next to it to show that what the spiral is, it's Earth spiraling through space, okay, and based on the different physics, the quantum mechanics, the optics, etc., which is outside of the scope of this conversation. Why it would affect human nature based on the torsion of the Earth's gravitational field, etc. We don't want to get into that right now. The point of this conversation is to show you how to import the data to use a spiral spreadsheet that you have with the raw data. So let me remove this. And the idea also, I studied astronomy as an elective in college, so I have stacks of astronomy textbooks and these white papers. If you want them, you can have them. You can have this one, for example. This one's called The Theory of Orbits and Spherical Polar Coordinates by Evans and Eckhart. It's an old paper. Explain that you use spherical polar coordinates when you're going to study the angular momentum of Earth going through space, etc. And then you can also do a Google search to understand a little bit more about spherical polar calculus and why it's used. The little dot that you see in that measurement, what we're going to use, that's going to be planet's Earth's position in 3 dimensions rotating through space, which is the spiral. So you can do your own little Wikipedia search on that on Google. So that's outside the context of this tutorial. So the first thing you want to do is open an Excel spreadsheet. You probably have the Spiral Calc spreadsheet if you're watching this. Get Spiral Calcs. Okay, so that's just Earth's orbit. That's a simple calculation showing its distance from the Sun in astronomical units. First you do is you take your sheet, open that, and you see the calculations. So we have the raw data. We're going to use right ascension, declination. We're going to use the longitude and latitude reverse position basis the center of the Sun, the North Pole angle, the North Pole adjusted angle, and then the distance. So that's going to be our raw data. So click, for example, click on row 8, column A, click data, and then from text, I have the spiral spreadsheet ready to go. As you can see, we have the spiral data in 10-minute increments from 1970 to the year 2100. I don't expect to be around that long, so, but you have it there. Maybe you want to give it to family members in the future, who knows. So I just download a ton of data. It took me a long time from the Jet Propulsion Laboratory. So let's use import data from 2019. We'll click next, and then we want to use comma delimited. Click next, and then general for our first column and hit finish. And then we want to import it into this spreadsheet. Take a second. Okay, so once we do that, we can see all the different properties from the data. We don't need any of that. So what we're going to do is we're going to delete these rows. It doesn't affect your text file. You can look through that if you wish. You want to delete these rows up into the point where you have the date and the data. So you have it in universal time data. I'm backward here with this. Universal time data. Let's remove these rows of data. Hit delete. And then we want to do is we want to make sure everything's aligned right. So I always click that top button here to do that. So that'd be up here at top right. And then what we have to do is we have to line the data. Okay, so in this case what we'll do is we'll insert a column. So in other words, I have to see the right ascension data from the spiral spreadsheet, and then the right ascension data and declination data from the NASA data. Those columns have to be lined up. So let's delete this, move it to the left. Made a mistake, go to the right. Insert right and then right. So in other words, we want to make sure that these column headings are the same. They all match. We do our calculations. So we want to make sure all these match. I'm going to open this up, and then some of these we don't need. So what I'll do in this situation, we don't need, we have NP angle, NP adjusted. To get the distance, so distance is delta. What I'm going to do is I'm going to insert another column here so that delta and distance are the same and they match. Insert to the right. Too much. So let's remove a column. Okay, so that's right. And then what we can do is we can eliminate that. We don't need the heliocentric longitude and latitude. Let's delete that. Excellent. And then I want to, we're going to use the velocity of Earth from the Sun. I can insert this, and I'm going to eliminate del dot. Insert this to the right. Okay. So this is actually distance. Distance from the Sun in astronomical units. Okay, and then we'll remove del dot. We'll clear this out, clear contents. Then we don't need SOT, we don't need these three pieces of data here. So to handle that, what we'll do is we'll move these three to the right. And then we'll delete and clear it out. Go insert to the right. Okay, now we'll clean this out. And I experimented with that data, but I don't anymore. And then we want to make sure that the distance. Okay, so you can go like this. Now we want to take the velocity of Earth's orbit. So what we want to do is we want to drag the velocity calculation. Okay, and these values aren't going to match. And the first one will be skewed because it's looking at L11 and there's no data there. So what you can do is you can clean that out. Just hit clear contents. Okay, and then clear this out. Anything we don't need. Alright, so that's going to be the velocity of Earth going through space. We can now double click that little corner button there. You see it right here? Double click that, and that will cover all 52,676 rows of data. Okay, then we'll keep doing that. We'll take the acceleration calculations and drag them. And then we have this erroneous. So this is the second derivative, so we can remove the second two, hit clear contents. And now you're looking at the acceleration, and if you know basic physics, acceleration is gravity when you break it down. I won't get into that. Now here are the spiral calcs. Alright, so you can see I'm using sine times cosine, etc., divided by 0.25 to get to my index that I created. And this goes back to using the spherical polar coordinates. I'll show you where that's mentioned here. Right here. So we're going to use the Cartesian coordinates right here. R sine theta cosine phi, y equals r sine theta sine phi, z equals r cosine theta. So we're going to use a spherical polar coordinate system, and then we see that in the spiral calcs. Now what I did to make it a lot easier, I divided the number by 0.25 to get to a whole number. Okay, so it's a long story, but I'm going to make it as simple as possible. I don't want to get into that. Okay, so we want to make sure we're referencing the correct cells, right ascension, and latitude from the object, which is the sun. And then we want to make sure that we're referencing the same cells to make sure our calculation is right. Right ascension and latitude, that's correct. And then we can drag this down, double click. Here's what I'll do. Because you don't have a reference, let's clear this out. It will not auto fill. So if we click that little bottom circle, it'll auto fill, and our count is 52,669 rows. And we can do this now with the whole data set. So the spiral in the XYZ frame is this image. Okay, so let's put the white background up. Now, this is that is the XY frame. So when you look at the spiral, you're looking down the z-axis, so it'll calculate. The sun would be on the left-hand side. The sun's this way. Okay, so you're watching. It's like you're watching Earth from a z0 position at the 0 coordinate, and you're observing Earth spiral through space. So, and that does include the counter rotation. Okay, which happens. That's the rotation of Earth's North Pole as it goes through space. So it isn't just going in a straight line, it's rotating. Okay, like this. Earth is spinning on a top, and that is what you see with the back and forth motion on the spiral. Okay, you see this forward, backward, that's Earth's north. It's I forgot the term, but it's rotating. It's using the North Pole as a position point as well in 3 dimensions. So what you see in that spiral is X and Y looking down Z. So when we look at Z, we can watch it from the side. And that's how you get the tunnel through the air effect. We'll get into that, but let's first take this off, get back to our calculations. So we want to calculate X, Y, and Z. We can take this whole data and copy and paste it. And it might take a moment. And then we'll copy all that. That's complete. There's a spiral, inverse spiral. Different calculations you may be interested in looking into. Calculate that. Spiral moving up and down and some of the derivatives. Now the envelope is the acceleration field. Okay, and the pulse is also the acceleration of Earth moving, pulsing, accelerating. So it's the second derivative which we know is gravity. So then there's an envelope, and that's a derivative. You can look at the calculations. So I'm just going to copy this all the way down, make sure it's covered, those points. Then I'm going to take the last row, double click to calculate everything, and it's done. 632,000 cells are now complete. Okay, so now what I'll do is I'll clean this up. I'll take out the items I don't need. For example, I don't need these columns. I'll delete those. And we can unify the column headings. And I'll go like this, take velocity, just copy all this. And now you have a copy, and you can paste it right here. Hit paste, bang. Get rid of any of the items you don't really need in those rows. Clear them out, and now hit clear. And now you have a nice, pretty, you can clear out these, we don't need these either. Clear contents. Okay, so you can see that we have a replication of the template. Now we have the times as well. The universal time, the data was gauged to Chicago time. So that'll be a topic as well, how to gauge it to your local time by moving columns down. Okay, but that's how you calculate it. Now let's take a look and graph some of the spiral action. Okay, maybe I'll step back a moment and explain now. What we have is the distance that's shown as del dot in the delta in the NASA data, which is the distance. Then we want the calculations actually come in column K, where we take the velocity, what's the velocity going through space based on astronomical units. Astronomical units about 100 million miles. You can Google it from the sun. So the way I formulated and download the data is the center of the sun is the static point, the measuring point to the center of planet Earth. Okay, that's the data that it downloads. So you're watching, so the sun is static, and then the Earth is moving as it goes through space, spiraling through space. So we have the first derivative is velocity. We need the second derivative. We want to get acceleration, which is a gravitational field. That's in column L. Sx, that's the angle, using the spherical polar coordinates, using x, right? Then you need y, then you need z. So I have two z calculations. Alright, so, and then you want to know the horizontal aspect. You can look at that calculation. Spiral radius, so I have a derivative now that explains what's the radius of the spiral. And I said a lot of phenomena at different points inside spiral. Radius 1 and outward as it expands or contracts. What's unique about the spiral, it's when you gauge the motion along z, it's not here's a book, Rotating Fluids, and it's green, so it's going to be Rotating Fluids in Engineering and Science by Vanyo. When you look along the velocity along z, you think it's going to accelerate. That isn't the same. A force vector is different. What's happening? There's two types of different vortexes that are occurring. What you're going to see if you study the spiral radius, and you study the spiral, you're going to find out that when Earth is accelerating along Z, the radius increases. And when it slows down is when it comes to the singularity or the midpoint. Which to me, I thought, when I first started studying the spiral, I thought the acceleration would be to the singularity, but that's when Earth is slowing down, coming to a point. So it's a free vortex and then a force vortex. So those two are different. Okay, so you can do your own research. In other words, the context of this conversation is just calculating the spiral first. Then we'll have some other videos explain some of the science and physics behind it. You can have as many of those books as you want and white papers on it that you want. Okay, so this is the square root of x and y will give you the spiral radius. Okay, and then I have different derivatives of that. And now you have the envelope, which is takes into account the acceleration. And I used a number 0.002 that made it clean, and it got it to 1 out to 4 to match the spiral radius, same as y. And then we have the pulses. So the pulses rotate and how fast. What's the acceleration of Earth getting yanked by the gravitational field. So in other words, what happens is that, if you know Newtonian physics, is that Earth gets pulled toward the sun and gets whipped in wanes, and at aphelion and perihelion, then it gets pulled back again. So gravity is an attractive force. So that those are the different pulses as it's moving. In other words, the pulse is the gravitational field that's pulling Earth through space. Okay? So let's make a quick chart and look at the spiral in X, Y, Z. And if you have an interest, I think I'll give you a download so you can track the actual times. Because once you want to graph the X and Y aspect of the spiral, we'll do that right now. In Excel, you have no way of knowing the time that it is. You'd have to manually go back and look at it, which was one of the frustrations I had when I first started doing it. We'll make a quick graph. So what you do is let me start over. Once you have the data in Excel, let me go up here. I'll go to the top. I don't want to waste time on that. We'll go right to the top. Let's make an XY spiral graph. So just copy this, drag it, make it two rows, 2 columns, drag it down, just an arbitrary amount, 10-minute increments. And then what you can do then is hit Insert, and you want to use scatter plot. So let's pull this down. Let's find a scatter, and we'll make it a smooth scatter plot. And there's our spiral. Bam! Once you do that, you go like this, move chart, and then put that on the sheet, call that chart 2. There you go. Now, you can see now that it looks oblate. Okay, the spiral looks like the time tunnel. The way you calculate that is you want to go into this axis, go left, format axes, and you want to make this -7 and maximum 7, and bam, like that, and there's the spiral. And I think the height has to be made to be 4, if I remember correctly. Go format axes, we'll make this -4, and then we'll make the maximum 4. That's wrong. Let's try 7. I'll have to go look at this and get clarity on that, but I think it's 7 by 7. Now let's go back to 5. -5, and then 5. And I think that was it. 5 by 7. Click, and there's your spiral. Okay. I think that was what it was. It was 7 by 5. Now we can see the singularity, and we can change the hit right click, format data series. You can manipulate the chart any way you wish. Change the characteristics, the colors. If you want to make this gold, make this gold. Okay. And then you can put the black dot. You can change whatever you want. Fill, we'll make the fill. We'll make it black. There you go. So you can play with that as much as you want. And there's a spiral, and you can see the radius is 4 high by 4 wide. What I'll do is I'll change the numerics here. Format axes will have the minimum is, the major is 1. There we go. Now the spiral is now 4 by 4. You get it? So the maximum radius of the spiral is 4. And the minimum is 0. So that's the singularity at 0. So what you're actually, nutation is the term. You're watching Earth spiral through space and nutate. So what I used to call the retrograde phase, that's caused by nutation, using those coordinates. So in other words, when you run this, you'll see a very strange phenomena slowly that it takes off and accelerates, and that's when the dots are wider apart. You can see it's got a very peculiar characteristic to it. It'll sit there and nutate, and all of a sudden it starts velocity increase and acceleration. It takes off and jumps, and that's when these dots are wider apart. Okay, so that's a pretty good, better than I expected. I didn't script anything, but that's how you import the data. The key thing is to get, let's look at the top, make sure that all the column headings are the same. Date and time, you could call that. And now since they're all, everything's done, you can clear out this dot. This is just my preference. I like to delete these columns, move it up. I can get rid of this, some of the coding that goes with the data. And we'll clear the content out. And then you're good. So that's 10-minute data for all of 2019. Okay, so if you want to, the problem you're going to have, and I'm laughing, is if you have a newer version of Excel, it can handle the calculation. When you start put years and years of data, the calculations, it gets harder to manipulate the data. So that's the end. There's some other elements from NASA. There are definitions of those terms. You can delete those at the bottom. They talk about the Solar Observatory, and the definitions of these things. You can read through those if you wish. STO, it's the angle from the sun target angle. As you can see, I got it from the Solar Dynamics group at the Jet Propulsion Laboratory. Clear that contents out, and you've got a pretty nice data set in 10-minute increments on the spiral for 2019. Now what I can do, I'm going to save this file, save as, and I'm going to go to my data and spreadsheets, 10-minute, and then I'm going to save this as spiral calcs 10-minute. Now, I'll broaden this out. I'm just going to save this spiral calc 10-minute increments. 2019, 10-minute. Okay, so see, spiral calcs 2019. Save it as that, and then I have it set up for 2019. Now we see spiral calcs 2019 10-minute. Okay. All right. Now, if you want, you can remove, you know, the upper column, but why? You know, keep it as a reference. Now you have the calcs, and you have all the calculations for 2019 in that spreadsheet. So that's pretty much it. And how to import data. I don't think I have anything in sheet 2. In sheet 2, I have the same items. You know, I could clean that up. This goes back to yeah, this is from January 7th to 2014 would be sheet 2. Same calculations. And then you can get rid of some of the technical details as well. But keep sheet 2 there as a reference. In sheet 1, you can go like this. You can rename it. Okay. Hold on. Let's go like this. Let's see if I go like this. I can go like this. I'll call it sheet 1. And I can rename this as rename. I'm going to call this 2019 10-min. How's that? I'm going to save. And then you got a 2019 10-minute spiral data set. That's just the data. Okay. You can play with it, and there are some other indicators I used as well in the past that I'll show you how to use in future videos. Okay, so that's just calculating the spiral and how you do it. How you import the data. You just click data again, then you hit import data. Oh, it's not showing anything right now. I think there's a glitch with that. Let's go data. I have to name a cell, so you just go data. I should be able to, I don't know why it's not showing it, enabling me to import data into a new spreadsheet. But data, again, the keystrokes. Why isn't it? I don't know what I did wrong. But again, it says data, import from text, and then go find it in the folder that you have, the year that you want to calculate. Alright, now you can do the same thing with the hourly data as well, because you have the hourly and the 10-minute data for your calculations. So that's pretty much it. You know, not a lot of razzmatazz. It's kind of technical. You know, kind of boring. So I hope you found that interesting. If you have any questions, you have my email address, or you can put comments below on how to import and create your own spiral. Okay, oh, here's what I should do too, because I did have an inquiry about it, a question about it. Let's make one a tunnel through the air. Okay, so let's look at our chart. Where is it? Okay, we got chart 2. Now let me go over to the other screen. Okay, chart 2. And what I'm going to do is I'm going to show you how to make the Z. Okay, so that's X and Y. Spiral X and Y. Get my head out of there. So that's X and Y. Now Z, let's look at the Z axes. That's going to be the spherical. Let's use O. So we're going to change it, and we're going to just change it from M, so you can go up there and then change it to O. You know, with in other words, the column is O. So I just went in there in the address bar, and no, that's the wrong one. I'll show you. It shouldn't be O. It should be P, because O is based on a derivative of B, which is acceleration, I believe. That's using rate ascension. And then Z, this one uses rate ascension, and this one uses G, which is, yeah, the latitude. So let's go look at, create the Z-axis with P. That's the spherical, so I call it SZS, which is the spiral. The other one you use with the acceleration. So let's change this to P. And we should see the tunnel through the air look on it from the side view. No. I have to change the coordinates, so the way you do that is you, we're looking at X is the y-axis, but that's not true. So we want to look at it sideways. We have to change Z would be viewing from the side. So we change these, make P is the horizontal. And then we make X, because we're viewing it up and down, we'll make that the Y, and that's M. And then we'll see, bang. Now we're watching Earth spiral through space from the side. Okay? Okay, so in this frame of reference, we're the observer. We are at a point, let's say, outside of, you know, watching, like watching an IndyCar race or a NASCAR race. You're watching Earth spiraling through space. You know, it's like this from the outside instead of looking at it head on. So looking at Z, Z is the horizontal, X is the height. Is that right? No, we're looking down. So in this case, our orientation would be looking down at the x-axis, looking down at it, okay, from above, an observer from above. So what we have to do is we have to go to N to watch it from the side. So M is X, looking down, because you're watching this motion from above, like this, looking at it. And now what we'll do is we'll change it to N to get the Y, in other words, from the side view. So I have all these things here, side view. Okay, now we're looking at it from the side, so we see the height is 4 by 4. Okay, so that's the side view. Again, I have Z, spiral Z, going this way through time. It's all inverted because I'm in the camera, but it's going this way in time, and then this is the height. Okay, so to double check that, I'll show you what I'm talking about. We're referencing columns P and N. So let's look at N as the SY frame. Okay, and then P is cosine G, which is the latitude. In other words, latitude. And this is longitude. So when we look at X and Y, we're looking at the longitude and the latitude combined together to make this goofy spiral. Okay, and then that would be M and N. We're looking at it head on. So that's from above. M and N, this will be the spiral, looking at it from behind. And again, the spiral is Earth spiraling through space. If you want to, take the time, you probably do, to understand the huge torsion that's pulling this planet through space, the numbers are just stupid. If you want to break it down to Mach, it's crazy. So there are times when it's at Mach 0, and all of a sudden the forward z-axis is crazy. Okay, so the planet will be at Mach 0. In like an hour and a half, it's at like Mach 5. 5 times the speed of sound. That's huge. The torsion and the calculus are so freaking amazing that are pulling this planet through space. It's kind of amazing. But that is planet Earth spiraling through space. Okay? And using spherical polar coordinates. Okay? Okay. So the dot you see is Earth. Okay? Now we can get into all the physics and the why and the variance of the magnetic field and going away and toward the sun, blue shift, red shift, and quantum gravitational optics and the effect of light on human behavior. That's outside the context of this conversation. Right? Okay. That's it. I try to keep it dry on purpose just because it's a really dry topic on calculating the spiral. Alright, so if you have any questions, comments, leave them in the comments section, or else you can email me and then we can go from there. Again, it was meant to be just a tutorial on taking your raw NASA data and applying the math and physics to the spiral data. Okay? Thanks. Any questions again? Comment below. Send me an email. Bye now.